A force is an effort that can cause a push or a pull. A force can change the shape of an object. Force can bring an object initially at rest into motion. It can also change the speed of a moving object. A force can stop a moving object. It can also change the direction of motion. It can be noticed that an object cannot change its state unless acted upon by an external force. That is, a force is required to initiate or stop the motion. Many forces act on a body simultaneously. For example, several persons may jointly make an effort to move a heavy cart. Here, each person applies a force on the cart, and these forces together produce some acceleration in the cart. However, the same acceleration can also be achieved if a stronger man pulls the cart hard enough. When a single force acting on a body produces the same acceleration as produced by a number of forces, then the single force is called the resultant force. When two persons apply the same force on the cart but in opposite direction and the cart remains at rest, the two forces are balanced. Or, if more than two forces are acting on a body producing no acceleration, the forces are again in the balanced condition. For example, if a car is moving with a uniform velocity, that is, there is no acceleration, in such a condition, the car is under the action of balanced forces. And the forces acting on the car are the force of engine that tries to speed up the car, air resistance, and the ground friction that tries to slow down the speed of the car. And if a set of forces produces a non-zero acceleration, the forces are said to be unbalanced. The overall force resulting from a combination of individual forces acting on the body is called net force. When a non-zero net force acts on a body, the body accelerates in the direction of the net force. One can push an object in different directions. This indicates a force has a direction. And if the same force is applied on a small and a large object, their speeds are different, indicating they have different magnitude. This indicates a force has a magnitude. Before 1600, normal state of rest was considered as the natural state of matter. Galileo, through his experiment, described a different approach to motion and the natural state of matter. When a ball is released on a smooth surface having two ramps, it attains the same height again. If we make the second ramp steeper, the ball again attains the same height after traveling a larger distance. And if the ramp becomes horizontal, the ball would never stop, as it would never reach the same height and continue to move with same speed. It shows that an object moving with constant velocity continues to move with the same speed and in the same direction as long as no external force acts on it. No net force means either no force acts on the object or forces act on the object, but they have their sum equal to 0. Both the states of motion indicate an important property of matter, to oppose any change in the state of their motion or rest. ability of an object to remain in a particular state is known as inertia. Thereby, Newton's first law is also known as law of inertia. In general, inertia is a measure of the response of an object to an external force. For example, let's take two balls of unequal masses. To move both the balls with the same velocity, one has to hit the heavier ball with a larger force. Similarly, if two cars of equal mass are moving with different velocities, it is obvious that the car having less speed can be stopped more quickly. Further, if two vehicles of unequal masses are moving with the same speed, then the lighter one can be stopped easily. These activities show that mass could be used to measure the inertia, and larger the mass, larger is the inertia. Inertia can be classified as the inertia of rest and the inertia of motion. In the inertia of rest, an object does not change its state of rest on its own. For example, a coin is placed over a card. Both the coin and the card are placed on a tumbler. On flicking a card, coin remains at rest for a moment, but finally falls into a tumbler due to the effect of the force of gravity. Similarly, in the game of carom board, when we strike at the lowermost coin with the striker with a speed, most of the coins remain at rest. Only the lowest one moves with the striker. Here, the upper coins remain in the state of rest, as no net force acts on them. In the inertia of motion, an object does not change its state of motion on its own. For example, when a train stops suddenly, the passengers sitting in the train are forced to bend in forward motion, since the upper part of the passenger's body remains in motion, whereas their lower part comes to rest. In the same way, inertia can also be classified as the inertia of direction. That is, when the object does not change its direction of motion on its own. For example, mud flying tangentially to the tire of the car. Newton's first law of motion tells us about the force and its effects. Newton's second law of motion tells us about the magnitude of the force. When we pull a body gently, a small acceleration is produced, and if we pull the body harder, more acceleration is produced. If we plot a graph between acceleration and force, it comes out to be a straight line graph with a positive slope. This shows that the acceleration achieved by the body directly depends upon the applied force. When we apply the same force on unequal masses, and it can be seen that on increasing the mass, acceleration decreases, and the graph between acceleration and mass again comes out a straight line graph, but with a negative slope. This shows that the acceleration attained by the body depends inversely upon the mass of the body. On combining the two conditions, acceleration depends upon the ratio of force and mass. In other words, force depends upon the product of mass and acceleration. When the net force acting on a body is zero, then the forces acting on the body are balanced forces, or the forces are in equilibrium. For example, when a book is at rest on a table, the force of gravity, that is, its weight, is acting on the book. Since the book is at rest, Hence, the net force on the book must be 0, or in other words, there must be a force that balances the weight of the book. That is, magnitude of this force must be the same as that of the weight of the book, and the direction must be opposite to that of the weight. This upward force is provided by the table and is called normal reaction or the normal force. This shows that forces always occur in pairs. Such a pair of forces that is exerted by two bodies on each other is called an action-reaction pair. Any of the two forces may be called the action, and the other will be the reaction. It is clear that for every action there is an equal and opposite reaction. This is also known as Newton's third law of motion. For example, when a heavy load is put on the head of a porter, the load acts on the head in the downward direction, and the porter's head pushes the load in the upward direction. These forces are equal in magnitude but acting in opposite directions, and hence forming an action-reaction pair.